Alright, a couple of my students have asked questions about if I'm given a pair of reactants, do I know whether they'll react or not? And at this stage we're talking exclusively about acid-base chemistry. So if I see a pair of reactants and I want to know will they react or not, I want to think about the acid-base properties of those molecules or ions. So in this case, I see we have a very familiar water molecule, and that pops into my head. The pK is about 16, so it's a moderately weak acid, and it could be an acid or a base depending on what it runs into. So you may know that water is amphoteric. The more you know about the characteristics of your reactants, the more likely you'll be able to follow the course of the reaction logically. If I look at HI though, this is something that from way back we learned is a strong acid. And now we're a little more technical, so we know pK is about -9, which is very, very strong. So my gut feeling right away is the strong acid is going to protonate the other molecule or ion, because that's what strong acids do. They donate their proton to just about anything. And to follow the course of reaction, I'm going to look at the mechanism. And mechanisms of these types of acid-base reactions all look and feel the same to me. If I'm going to say that the HI being a strong acid is going to be the acid, then I'm going to have to consider the water to be the base, because in order to have an acid be an acid, it has to have a receiver for its proton, which would be the base. So here's a lone pair of electrons and the base, and the way most bases work in this type of chemistry is the lone pair on the base is going to go pluck off the H plus of the acid, and then the bonding pair that holds the acid together is going to turn into a lone pair, then become part of what we would call the conjugate base. So this pair of reactants can react in this fashion. When the water grabs the H plus, then what was a bonding pair turns into what was a lone pair turns into a bonding pair, and that's going to give me the positively charged hydronium. So we've added the H and the plus to the water, making the H3O plus, and then as the iodine loses the H plus, that's going to make iodide the anion. And the question of will this reaction work or not will boil down to where's the weakest of the acids. So we're going to compare the strong acid, which is the acid in the reactant side, to the conjugate acid of the base reactant. So the water, when it grabbed the H plus, turned into its conjugate acid, the hydronium, and if the hydronium has a pK, which we should know, pK is about -1.7, we can compare the acidity of the hydronium to the acidity of the HI. The stronger acid is going to react and force the reaction in the opposite direction. So looking at these, the HI is way stronger than the very strong hydronium. So this is the weaker of the acids, and since it's on the product side, then this is going to be product favored. And if you reacted hydroiodic acid or hydrogen iodide with water, you'd have a vigorous reaction to produce hydronium and iodide in the solution. So the reaction is going to favor the formation of the weaker acid, and pKa -1.7, although it's a very, very strong acid, it's weaker than HI with a pKa of -9. So given these reactants, I can look at the mechanism to figure out what the products are by doing a proton transfer from the acid to the base, and then by looking at the relative strengths of the acid in the reactant side and the conjugate acid in the product side, I can decide which is the most stable combination, and since hydronium is weaker than HI, the products will form in this reaction. If I had drawn some potential products and found out the product is more acidic than the reactant, then nothing would happen, and we'd say it's reactant favored. So that's an example that's fairly typical in organic chemistry. Even though this is a very inorganic example, we'll do an organic one a little later. It's how to approach this, to look and say, hey, what's the acid, what's the base, follow the mechanism to find out what the products are, and then compare the strengths of the acids in the reaction to see which is favored. Alright, another acid-base type question is, which is the stronger acid? And why? Right, so if I look at phosphine versus ammonia, again, a very inorganic example, but the atoms don't know whether they're carbon or not, they just do their thing. So the principles that govern inorganic chemistry also govern organic chemistry. And when we're looking at acidity, we're looking at, is the hydrogen going to leave as an H+, and the characteristics of the atom it's directly attached to are really important. So the size, the electronegativity, and the hybridization of the atom directly attached to hydrogen are all important. So when I look at these, I see nitrogen and phosphorus are in the same group in the periodic table. So nitrogen is going to be the smaller atom, and phosphorus is going to be the larger atom. And when we looked at representative examples, we looked at HF for another smaller second row element. So second row element HF versus HCl. And the pKa's 3.2 for HF, -7 for HCl. The larger atom corresponded to the stronger acid. So likewise, the larger phosphorus is going to make the phosphine the stronger atom. So we're looking at this as a size effect. And in this pair, we're going to say pH3 is the stronger acid because phosphorus is larger than fluorine, and larger atoms attached to hydrogen make stronger acids. So we have a nice representative example to illustrate the size trends, and now we see that in play. And if we wanted to get quantitative, it looks like we decrease the pH by about 10 units, or the pKa by about 10 units, going from here to here. If we know this is 35, we might guess this is maybe pKa 25. So we definitely are going to expect the phosphine to be a stronger acid than the ammonia, because the phosphorus is a larger atom than the nitrogen. And with respect to these effects, if you've got a pair of compounds, you want to see, is it the size of the atom directly attached to hydrogen that's different between the two? It might have been electronegativity, which is a weaker effect, will have less impact. It could have been the hybridization of the atom directly attached to hydrogen. There could be resonance, there could be inductive effects, or there could be a charge difference between the species you're looking at. In this case, because nitrogen and phosphorus are in the same group, it should be clear that phosphorus is larger than nitrogen, and that's going to be the most important difference between these two molecules. So there we go. Which is a stronger acid? The phosphine by quite a bit, because the phosphorus is a larger atom than nitrogen. Let me fix this little handcrafted typo for you. Phosphorus is larger than nitrogen, although it is larger than fluorine. That's not the comparison we were doing. So phosphorus is larger than nitrogen. The larger atoms attached to hydrogen make stronger acids. Alright, so one more example of a pair of things. I was going to say a pair of molecules, but this one's an ion, where we have a potential acid-base reaction. This is a very organic example, so everything here has carbon in it. And when I look at these, I have a neutral molecule and an anion. And one of the things that is a good thing to remember is that ions are often bases. Bases. So this one could be a base. And the other thing you should recognize is that CH3 minus is the conjugate base of methane, which is our weakest acid. So our weakest acid's conjugate is going to be the strongest base. So if you recognize that, you're not going to say base question mark because it's just an anion. You're going to say strong base because it's the conjugate of methane, and we know about methane. And even if you didn't recognize that right away, you could explore if this anion could grab an H plus off of this, what would the products look like? So let's go ahead and do the typical acid-base mechanism. The lone pair on the carbon is going to go fetch off an H plus, and then the bonding pair is going to become a lone pair. So when we do that, we get the new carbon-hydrogen bond, and that makes our good familiar methane, which is pK equals 50, right? pK equals 50, so very weak. And then when we deprotonate the ethylene, which was pK equals 44, then you get most of the molecule remains unchanged. But now the bonding pair that used to hold the hydrogen on turns into a lone pair, and because we lost something positive, we now have a negative charge on this side. So when we compare the two acids, this is forced to be an acid because the base is so strong, and then the base, when it grabs the H plus, turns into the conjugate acid. And now we look and see that the product pK is higher, or the product is the weaker base, so this is product favored. You always favor the weaker base. And so this reaction will go. So this base is way strong enough to react with this potential acid to create the more stable methane. Now, if you ask a new organic chemist, sort of a novice, to make the ethylide, or the ethide, I guess you'd call it, if you wanted to make this anion, and you said, okay, find something that'll deprotonate this molecule so you'd get this ion, a lot of people would think, oh, okay, so I just need a strong base like hydroxide, right? So it's common for people to say, yeah, hydroxide's a strong base. If I need to deprotonate something, I'll throw in some hydroxide. It'll go get the proton and make our product. And then if hydroxide grabs an H plus, it makes good old water, and it'll make this organic anion, right, which we would successfully make if we threw the methyl anion in with that potential acid. Then we'd have enough base power to deprotonate this. Now, although hydroxide is by many standards a strong base, when we try to deprotonate this acid with pK equals 44, our base turns into a conjugate acid with pK equals 16. Now, pK equals 16 means it's much more reactive than pK equals 44, so this is the stable, less reactive of the two acids in our comparison. So this is going to be reactant favored, and in reality nothing will happen. It will favor the reactants because if you did have water and it hit this base is super powerful and would deprotonate the water and make what we thought might be our reactants. So the moral of the story is this is too weak to make this reaction happen because its conjugate acid is strong relative to the thing that we're originally trying to deprotonate. So the less reactive, less acidic compounds are going to not react unless you throw a really strong base at it. And hydroxide is just not strong enough, as witnessed by the pK of the product you get when we react hydroxide. So hopefully this makes some sense as to which reactions happen, how to write the products by moving the proton and doing a simple acid-base mechanism, and then how to describe what's happening in the language of organic chemistry, that if the weaker acid is on the product side, then your product favored and the reaction will happen as written, and you'll get these products. If the weaker acid is on the reactant side, then you're essentially going to have no reaction because you've already got the stable combination, and if it's stable, then nothing will happen. So hopefully this is helpful and answers the questions I was asked fairly clearly.